Morning, everyone. So yesterday we looked at the benzene functionality. This would actually put us in the aromatic family. We see the formula benzene is C6H6. It has many degrees of unsaturation because it's actually lost a bunch of hydrogens. It has one ring and the equivalent of 3 double bonds. Remember, benzene here actually demonstrates resonance. It's actually the resonance that actually gives it stability, and that actually allows benzene to actually not do the regular addition reactions, substitution reactions as we would expect before, but we'll actually learn a new type of substitution reaction for this compound. So let's just finish off with benzene. There's a little bit more to do with reductions afterwards, and then we'll just summarize it all on one big mind map. So looking at benzene here, this is the first time we're actually seeing an electrophilic substitution. Instead of like an alkyl halide, a nucleophile actually comes in to actually replace itself with a halogen group as a leaving group, SN1, SN2. This time here is actually an electrophile that actually gets substituted. So we do represent this benzene here. It is a 6-carbon circle here. That would just be a cyclohexane without the circle. This one here is actually showing us the resonance. It has the equivalent of 3 double bonds here, but in resonance, with the double bonds being in alternate locations there. There is conjugation because a double, single, that sort of pattern, but effectively these guys here work out to all equal bond strengths. Because it's the resonance that actually adds stability, I want to do my best and I want to keep this ring as long as I can. So if you imagine for this ring here, we refer to it as pi delocalization. These would have otherwise been pi bonds. So you can make a note here. Pi delocalization gives that resonance stability. Things that have resonance will be more stable compounds. So if I just focus on one single hydrogen on this benzene ring, also referred to as a phenyl group, what can happen here is we're taking here an electron-rich environment. This electron-rich environment is going to attack something that is relatively positive, right? That one there is going to be an electrophile because that one there is seeking out negative density, although we draw our arrows always from where the electrons show up. There's a sort of temporary sort of middle ground here. We're going to have a situation where the carbons are still holding on the hydrogens, but now that you've created a bond with the E group here, the carbon here would be slightly positive. I'll do this in a little more detail with you later on. That temporarily breaks the resonance stability, right? So it's going to end up still having a little bit of delocalization, but unfortunately not all the one around the ring. What's going to happen then is I want to regain that stability around the ring. I'm going to then lose this hydrogen. So these electrons are going to come back down, and we're going to end up seeing our electrophile has actually substituted its way onto our benzene ring, and phew, we end up back with that stability. So benzene actually undergoes a new type of reaction, electrophilic substitution reaction, where a hydrogen, right, benzene only had C6H6, so if it wasn't for the carbons, the rest of them are just hydrogen. Those ones are substituted by an electrophile. So the electrophile is the thing that replaced versus an alkyl halide, it was the nucleophile that actually came in to replace. So there's a different group here, and then we regain the stability of the pi delocalization. The incomplete circle inside the ring shows a loss of symmetry, so it's sort of unstable there. And we can do this to actually introduce different functionalities onto the benzene ring here. As long as we have an electrophile here that is liking of this electron density, we can choose whatever electrophile group that we want. The H group that leaves will end up leaving as a H+. Okay. So first thing here is sort of a middle step. I just want to show you a mechanism of something called nitration. We're going to create a compound here called nitrobenzene, and then they want you to know the reduction for nitrobenzene. So this is sort of like a precursor step here for a nitration process. Okay, we are trying to add an NO2 functionality here onto the benzene ring. Right. So this one here, I want to end up having this guy in the presence of two really strong acids, HNO3 and HSO4. This one here is actually referred to as a nitrating mixture. I'll show you the mechanism of this in a second here. And basically, when it actually reacts with this nitrating mixture here, we will end up having an electrophile substituted onto the benzene ring here. That's actually an NO2 group that we're going to use later on. So this first reaction called nitration is for us to form nitrobenzene, and later on I'll show you a reduction reaction for there. So first thing that has to happen here is I need to tell you what happens in this nitrating mixture. This part here is actually fairly interesting. So first, for your nitrating mixture, for this red portion here, I'm going to take HNO3. So I'm going to draw a Lewis picture for this. So HNO3 looks like this so far. Okay, if you did your formal charges, you could have this side relatively negative, relatively positive, although overall you're neutral. This is weird that I'm actually not in solution. I'm not in water, right? We found in our redox chapter water was really annoying. I'm actually mixing an acid into another acid solution. So sulfuric acid in a very similar fashion here. We have HO sulfur. It's almost like a sulfate structure. Right? This time we have two very, very strong acids. Well, like we said in our acid-base chapter, they can't both be acids. They can't both be willing to toss footballs. Whoever does it better ends up donating the proton. Back when we were in water, we had the leveling effect. Oh yeah, in water, we basically remove the same H on both sides. Everything's equivalent to one H plus molecule anyways. They're equal strength. This time, when you mix HNO3 with the HNO2, the sulfuric acid here is actually a stronger acid. So this one here, not only it was strong to begin with, but between these two strong acids, the sulfuric acid here gets to do its job and actually gets to donate its H+. Now back in the acid-base chapter, I may have pointed, oh, the H group then leaves like that. Remember in this organic section, we always want to talk about electrons that are doing the moving. So we're going to have, because this H is going to be the easier removable one, this oxygen group here ends up picking up that H there. This bond here essentially breaks, so the electrons go back on the sulfuric acid here. Let me just try to keep it color-coded for you. This mechanism you do need to know, so make sure you pay attention to this part here. So we have temporarily, I have HO. I've then grabbed another hydrogen that didn't used to be mine. In total, this one here would have been picked up as an H+, so therefore overall this one here has a plus charge. And then we've ending up sort of dislodged a HSO4 minus. That's going to come back later on. So far we just said as a stronger acid, it donates its proton over. And then what's going to end up happening here is because of that positive here, I don't like things being positive. What's going to happen is this bond here is actually going to break, and it's actually going to release off this water molecule. So let's try that here. Let's take this bond here. Let's give both of our electrons to the oxygen to make sure everything is sort of matched up. This oxygen here ends up forming a double bond. So then we end up creating a water molecule. So HO, we ended up making an H like that. We have finally made the thing that I wanted, which was this really, really reactive species N-double-bond-O, N-double-bond-O. Okay. This one here is the very reactive. We call it a nitronium ion, right? NO2. And this one here has an overall plus charge. And what about the HSO4? The HSO4 here could steal an H plus back from any of these guys here and actually reform sulfuric acid, but the emphasis here is we ended up making our nitronium ion. And it is actually that nitronium ion that's actually going to be the electrophile. It has that partial positive here, and when benzene actually attacks the nitronium, we end up being able to add this NO2 across the benzene ring. So that's one step you do need to note. Second step here, sort of the mechanism for this step. We have our benzene. I'm going to focus on one hydrogen. In fact, there's actually 5 other hydrogens here. When I take this very reactive nitronium ion, again, this nitronium here is currently an electrophile. It has the electropositive part, relatively positive portion. The delocalized ring here, it's always negative attracts positive, but because the electrophile is going to be added, we call it electrophilic substitution. So temporarily what happens? Again, I'm drawing arrows for what the electrons are doing. 2 electrons will end up bonding with the nitrogen group temporarily to hold the hydrogen and the nitrogen group. For a little while here, this electron needs to go over because the nitrogen can't expand its octet. We're going to have a sort of middle molecule here. We have a ring where we have the hydrogen group, and we've now sort of added on this nitrogen. The one side is still just double bonded, no problem. The other side here is the equivalent of single bonded like this. Overall, there's going to be a relatively negative side and a relatively positive side here. That's our nitronium ion. This is when your benzene ring actually is temporarily losing a little bit of that resonance stability. I'm going to show you this. It's a positive charge spread somewhere around there. And then because this is substitution, I end up kicking off something. So what's going to end up happening here is this electron here ends up going back down to try to restabilize the ring. And then we're going to end up having the electrons here. These electrons will end up coming back down this way. So what we're going to have finally is a NO2 group functionality here on top of this benzene ring, and we call this one here nitrobenzene. This one here is ending up releasing off an H+. We're going to see a quick reaction with nitrobenzene shortly, but I did want to show you one more detail here. You do need to know this mechanism for creating the nitrating mixture, and then using that nitronium ion here to end up forming nitrobenzene. I just want to show you a little bit more detail for this middle step. What do we mean by this sort of dotted line, the positive spread it like that? In fact, that's actually just showing you resonance. So I'm just going to do it down here. There's a little bit more room. So I'm going to have my benzene ring as the equivalent of 3 double bonds. We have E for an electrophile. That was a relatively electropositive part. We do our attack. So the double bond here attacks this electrophile here. Temporarily, we end up getting our benzene ring here. I now have a hydrogen and our electrophile temporarily holding on to that electrophile. The electrophile here overall has a positive charge here. The question is, where does that positive charge go? The positive charge here could actually be down here. Well, if I have a positive charge there, I can't actually have 3 double bonds, right? I've actually used these 2 electrons to end up creating a bond there, and then we end up having this orientation. But we actually have this in resonance, where I could actually have this positive charge here seemingly moves around. What if my double bond here pushed over, and this double bond here pushed over a little bit as well? So let's just draw that picture first. So we're going to have our positive would have been actually down here. I have my double bonds on opposite sides, so E and H like that. Or better yet, if I have another double bond here equivalent and moving down here, then the positive charge moves up. All these structures here are actually in resonance. So we have the equivalent of the double bond here, here, and we have the positive. And that's actually what we mean by there's only a sort of a partial delocalization left over, but this part here is actually showing you the resonance for where the positive charge is. Okay? It's not really 2 double bonds, it's not really a positive charge, but it's shared evenly around the rest of this ring here until you manage to kick off the hydrogen. When you kick off the hydrogen and release that off, then I can reform the resonance around my 6-carbon ring there. Okay? So again, benzene, it doesn't react like other alkenes because of this delocalization. It does what's referred to as electrophilic substitution. Okay? That is a reaction that you definitely want to know. How did you create nitrobenzene using our nitrating mixture, concentrated HNO3, H2SO4, our nitrating mixture there. I'm going to show you why bother create this nitrobenzene. One particular reaction to this one here is the reduction of nitrobenzene. So I'm going to demonstrate that procedure for you. We'll talk about reductions in general, and then we'll go from there. So take this the NO2 replaced H group, and let's talk about the reduction of nitrobenzene. This is another mechanism for you to just memorize. I just memorized this. This part here won't actually be on our mind map, right? Because this is very specifically looking at a particular functionality of benzene. We've been seeing reduction. We knew from our redox chapter, reduction means Leo line says gain of electrons. Sure, you can try to dig through and try to figure out who's actually gaining electrons, but we're actually going to use our other definitions for reduction here. Usually a reduction involves a loss of oxygen. And if I sort of replace oxygen, I just assume what's replacing is actually hydrogen. So sometimes you can think of it as a gain of hydrogen. So if I end up seeing a compound, well, I have more H's equivalent than I had before, it probably meant something has undergone a reduction reaction. So reduction of nitrobenzene. So I've created this one here. Step 1 actually takes our nitrobenzene. I had done this sort of hard process. I substituted the NO2 group on this molecule here. This one here also has some fancy reacting conditions. We're going to have to use tin as a catalyst, right? we're going to use concentrated hydrochloric acid. We're going to need to have a little bit of heat, and I'm going to actually undergo it using reflux, get the reaction to go completely. Again, you don't need to know the mechanism of this one here. This one here, it won't do any more substitution on the ring, but this one here will actually help to reduce this NO2. It's going to add more hydrogens instead of the oxygens, and therefore we're ending up with same benzene ring here. That functionality is still there, and we end up with NH3 as a positive. Once we have that guy there, step 2 takes this one. I'll just do it down this way here. So step 2 is actually involving, let's add a hydroxide group. Since this one here is an H plus group, the hydroxide can pick off one of these hydrogens. So the details there are, imagine this NH3 group. Imagine if it were like NH2 and a hydrogen like this, it has a relatively positive like this. And then what's going to happen here is my hydroxyl group is actually, it has a bunch of lone pairs. It's going to donate its lone pair, pick off this hydrogen, and those electrons end up going back on the nitrogen. We're going to end up forming a nice precursor here. We have our phenylamine here, and we end up getting an amine on this benzene ring, so phenylamine. Okay. Because this has to take place in 2 steps, you notice it's sort of contradictory because it's like, oh, we actually added acid and then we add base. These are definitely not mixed in the same mixture, right? Or else the hydroxide would just neutralize the acid and neither of these reactions will occur. How we can actually summarize that there is we can actually say, okay, so I took my nitrobenzene, so this is the net reaction. I took my nitrobenzene. You can actually use numbers to say, step 1, reactant number 1 is in tin using concentrated hydrochloric acid, using a heat treatment under reflux. And then as a totally separate step here, you're going to react it with some base here just to pick off that H positive, and then we end up getting phenylamine. And that's now been reduced. You can check oxidation number yourself, but I see just in general, well, if I replace oxygens now with hydrogens here, that generally talks about a reduction mechanism. Okay? So benzene is strange. It's sort of a case by itself, but you do need to know those 2 mechanisms. Okay. We're going to finish off this lesson here. I'm going to talk about reductions a little bit more in general. Right? We talked about alcohols being oxidized to aldehydes, ketones, to carboxylic acids. We're going to use reducing agents to also reduce those ones, just like I'm reducing benzene here. And then we're going to finish off with some synthetic rubs. So that just introduces us to a little bit of reductions involved here. So I just want you to recall here. So stepping away from benzene now. Recall the oxidation of alcohols, right? So we had, depending on my degree of alcohol here, a primary alcohol could have been oxidized. In general, we say plus O for oxidation. If you do a distillation process here, this one here ends up forming an aldehyde. The aldehyde here has lower boiling point than either the alcohol starting, or if you completely oxidize this one fully goes to carboxylic acid, right? Or if I had a secondary alcohol upon oxidation again, so plus some oxidizing agent, this one ends up forming a ketone. If you remember the oxidizing agent here, you could hypothetically use potassium permanganate, but usually it's a little bit too strong, so usually we just use acidified dichromate. Right, so we have H plus and we have CR204. What we can do here is we can actually, CR207, we can actually reduce these back. So oxidation is going left to right. Reduction is just trying to, well, let's undo these reactions. It wasn't reversible, but what if I wanted to take my aldehydes or ketones and bring them back to alcohols? Or what if I also wanted to hit carboxylic acid, maybe go through aldehyde, but also back to an alcohol here? What if I wanted to do these reduction reactions? So just a quick section on here. So we can reduce carboxylic or aldehyde and ketones back to alcohols using different reducing agents, right? There's more options that I'm going to give you here, right? We had a whole redox table showing you a lot of different strengths of reducing agents. I'm going to give you 2 really common ones. The first one here is super strong, okay? The second one. Let's do the more milder one first. So sodium borohydrite. This is just another reacting condition. If you drew the arrow the other way, you should be able to note this one. So this is NaBH4. That's a little bit weird of a compound. Boron usually has an incomplete octet. It usually only has 3 attachments. Here's boron temporarily having 4. That's why we're going to see it actually produce an H- ion. This one here is in aqueous alcoholic solution. Or the stronger one here is actually our lithium aluminum hydride. This one would be LiAlH4. And this one here has to be in anhydrous mixture. Water actually interferes a lot, just like it did in our redox chapter. It interferes a lot with our organic chemistry here. In anhydrous conditions, so no water present, usually we use a common solvent here called dry ether. The dry doesn't mean it's not liquid. It is still a liquid. It's still, it is a mixture, right? But there's no water present. And then as a second step, that's where we need our 1 and 2 again, followed by aqueous acid. So in the first step, we wanted it to be dry, no water, right? And yet in part 2, we actually want it to be aqueous, so yes, water, and also acidic, right? Again, you don't need to know the mechanism for this here, but just a little bit of detail. Both of these ones here, so both reagents is just a fancy word for reactant, okay? Both reagents produce the hydride ion, the H- hydride ion. And it's actually this H- that's going to add to my oxidized aldehyde, ketone, whatever, and bring it back down. So hydride ion produce, which acts as a nucleophile. It's going to then sort of add its way, reduce the oxygens, add more hydrogens onto the molecule. The sodium borohydride, so NaBH4, tends to be milder, tends to be a little bit more safe to work with, so can only reduce aldehydes. Aldehydes become primary alcohols, or ketones. Ketones become secondary alcohols. So those ones there, sodium borohydride would have no trouble reducing NaBH4 like that. Sodium hydride has no problem bringing this one backwards. But because carboxylic acid is so fully oxidized, I need something that's actually stronger as a reducing agent. This one here that I'm going to give you, not only will be able to reduce this, it's going to reduce it so well that you actually won't be able to stop at the aldehyde step. So we know how to reduce aldehydes and ketones. We need the stronger lithium aluminum hydride, LiAlH4, to reduce carboxylic acids back to alcohols. Also primary, right, because it was only the primary that could fully oxidize to form there. But the emphasis there is, but we cannot stop at the aldehyde phase because it's such a strong reducing agent here. Right? So if, for example, I take ethanoic acid again, so CH3COH, really dilute sample of this one here would be vinegar. Essentially what I'm doing is I'm trying to do a plus hydrogen. Plus hydrogen indicates to me here this is going to be a reduction. This one here is our fully oxidized form here. If you did sodium borohydride, it's not strong enough to actually reduce this. This one here actually needs to have the LiAlH4. This one here also took place in 2 steps. First one, the thing that's going to give me my hydride nucleophile is LiAlH4. I need to mention that this is in dry ether, right? No water present. And then as a totally second step, then you can put in some H+, but that one there can be an aqueous in water. You do step 1 first. You sort of run it almost to completion first, and then you do step 2 as a totally second mixture. You cannot stop as the aldehyde stage. The aldehyde would have been chicho like this, right? You would have gone straight through there, and you'd end up forming our primary alcohol. Okay. So if you want it in words here, we have heat with lithium aluminum hydride in dry ether Then, right, I just want to just emphasize here, it's always 2 steps. Then follow with aqueous acid. Okay. At that point here, we have all the connections that we want on our mind map. I'm going to draw for you this mind map here. I'll give you a digital copy of this as well, just in case you miss anything here. And then based on this map that we're going to draw, we're going to be able to do one more style question. Okay. So I would encourage you just pause the video, see if you can draw the mind map just for practice again, but see if you can even add in these reduction steps here. So let's just go through here. We have our alkanes. Alkanes react with oxygen. They burn to form combustion products. You can add Cl2 or Br2 in the presence of UV light. That ends up forming an alkyl halide or halogenoalkane. Either name is fine. Then we have our alkenes. Alkenes have a C-double-bond-C. I can hydrogenate them. So in the presence of H2, we usually use nickel as a catalyst, slightly hotter than room temperature here. We can form a halogenoalkane here by adding an HX electrophile across the double bond. That occurs at room temperature. I can add an X2, also occurring at room temperature here. That ends up forming a dihalogenolalkane. It's an alkane with 2 halogens. It can react with other alkenes and end up forming a polymer. So linking of many monomer units. This part here, again, super important. It is an equilibrium. So concentrated sulfuric acid. This one here, we're going to add water across the double bond. The acid actually adds first, and the water substitutes place for it. That ends up forming our alcohol. These ones here all burn, so we're going to have plus O2, plus O2. Alcohols, depending on their primary, secondary, tertiary category, we're going to use acidified dichromate here, Cr2O7, like this. First degree, second degree, third degree. They always test you third degree here, no reaction. I can't break apart the structure. Second degree here, we can oxidize it. So that's going to be using heat and reflux. That's going to end up forming a ketone, a carbonyl group. Primary, if I want to stop it midway, I do heat and distill. Heat and distillation will end up forming an aldehyde, while if I do it completely here, heat and reflux, basically get it to go to completion, I get a carboxylic acid. We then switched over to our alkyl halides for substitution reactions. If I have a nucleophile of OH minus, the OH minus can replace that. That just happens at room temperature. I can react with the ammonia or amine functionality to end up forming an amine. I can react it with the cyanide, so end up forming a nitrile. We had our pesky condensation reactions. A condensation reaction was between carboxylic acid and alcohol. These two here end up forming an ester, while that one here also needs to be acid. For the other one, carboxylic acid and our amine, this one here ends up forming an amide. That one just usually needs heat treatment. Okay, and now what I've done is I've actually added in the reverse processes for reduction. We can take our ketone and aldehyde back to the alcohol. That's going to be through the reduction process. Let's just use brown here. So this one here, you can use sodium borohydride, so NaBH4. For the NaBH4, you look at the reacting conditions here. NaBH4 has to be an aqueous alcoholic solution. So you can say aqueous alcoholic. That works for this one, as well as ketone back to alcohol. If I want to go from NaBH4, if I want to go from carboxylic acid, the fully oxidized one, back to the alcohol, this one here needs the stronger one. It needs 2 steps. First step, lithium aluminum hydride in dry ether. Right? And then second, we're going to throw in that H3O plus aqueous again. Okay? So that one there is important that you'd show in 2 steps. Okay? So now we've sort of done the mechanisms and the reactions that we're interested in. Now we have a lot of ways to actually interconvert from one family to another family. So this leads us into our last style question here. This part here is going to be referred to as a synthetic route. Okay, have that mind map handy for yourself. Okay, what we're going to try to do is we're going to try to create a pathway, a synthetic route, also referred to as retrosynthesis. Depending on what our target molecule is, we want to actually design a pathway to convert one thing over to the other thing. So let's just do this by way of example here. I want you to design a reaction pathway. A reaction pathway to make. We have a target molecule in mind. I'm going to have a C, CH3, CH3, O, C, double one O, CH3. Let's say we have this. Okay. So maybe I'm in the pharmaceutical business and I want to create this one here. I would need to watch out for like R and S isomers and things like that as well. But just for us, we sort of have a target molecule in mind. This is what I want to end up creating. Okay. Right now here I haven't really specified what my reactants are, but the whole notion here is, well, I want to know what should my reactants be, what should my precursors be, and what are my conditions that I need to actually, it may be actually multiple steps to end up getting this target molecule. Our strategy is actually to work backwards, just one step at a time. Take a look at the target molecule. Take a look at what would the precursor of this molecule be. What would the molecules be right before this step? And then what would be the molecules right before that step? And what are the molecules right before that step? And we're actually sort of going backwards and actually defining our method and going back the opposite way. So let's try it out here. A good way to do this here is actually recognize what family we're in here. Because we have the C1100, we are in the ester family. If you look back at our mind map, we only were able to form an ester from a carboxylic acid and an alcohol. So I just need to tell you here, well, what is my carboxylic acid and what is my alcohol? The carboxylic acid here is the carbon side, so this one here. The molecule right before this one here would have been ethanoic acid. The other one here would actually have to be CH3, CH3. This one here would have had to have an OH like this, so that, just check your work here, so that if I pull off this O and the H is like that, if I end up losing this water, I end up gluing the CCC to this purple part, and therefore everything's good. Okay, so you see this is the sort of next closest step here, and now what we can do is we can talk about, okay, well, what are the steps needed to make these ones? Let's do this just one by one here. So this one here is already an alcohol. Maybe this alcohol needed to be made from a alkene. So maybe the step before this was I actually took propene. Right? I'm just sort of redesigning, going backwards here. Maybe it was a propene like this. Right. So this is prop-1ene. And then what would I need to do to actually cause it to actually add water across? Remember, this one was a reversible reaction. You would need to note the reacting conditions. So again, concentrated sulfuric acid. That's needed for this first step as well. So concentrated sulfuric acid. Right. But we're trying to add a water across the double bond here. So the acid adds first. Watch our Markovnikov's rule here. If I just did this one plus water, I'm trying to add an H and an OH like this. Well, which side does the H add to? Markovnikov says the carbon here that's more highly substituted, if the H adds to this carbon here, I end up forming a more stable carbocation here. When I do that, perfect, then the OH adds perfectly, and then we'll have the OH in the middle. If we actually wanted to have the OH on the ending, Markovnikov's rule wouldn't actually work. So just a reminder here. So this is Markovnikov. Markovnikov would create propane 2O, right, which is, fortunately for us, what we need. For us, that's probably as complicated as it's going to get. So we have an alkene here. How about forming this carboxylic acid to begin with? Well, carboxylic acid here is the sort of fully oxidized form of the alcohol. This one here would have come from a primary alcohol. So this molecule by itself, I'm just sort of working my way backwards again. Maybe at one point here I had my aldehyde, so my CHO, and then CH3 like that. I need to sort of further oxidize that one there. This one here would have come from my primary alcohol, CH3. Maybe I should draw that out for you so you know what I'm doing. Double O like that. It actually is bonded C and just an OH group. So H, H, and OH. Right. This one here could very similarly have been formed from an alkene. So let's say ethene, C-double-bond-C, and then this one could have been concentrated acid in equilibrium, adding water across the double bond, and ended up creating this water grouping. Okay. So you see we're sort of working our way backwards. What did I need for the oxidation process? Sure, you could just say plus O, but it's a good idea to actually tell me what are your reacting conditions. What we needed was acidified dichromate, H plus, Cr2O7 minus 2. We needed a heat treatment. I don't want to stop at the aldehyde stage, so I needed to reflux. Okay. Now, I've sort of done this sort of in full detail for you here. I sort of worked backwards as much as I could. Usually they say they're going to max out only four steps to do a series. Okay. So let's just try through one more question here. Your mind map will come in a lot of handy here because this will show you all the interconversions between the two of them. So I want you to design a reaction sequence. So design a mechanism or a series of steps to convert. They might even specify what your reacting conditions are to convert propene into propanoic acid. Okay. So again, I encourage you just to pause the video, try it out for yourself. Okay. I would draw out the molecules. So propene here. Prop means 3 carbons. I would normally say prop-1-ene, but there is only one place for it, so chemists are lazy. I'm starting with this molecule. Whatever I'm not showing you here is just hydrogens. I want to end up getting it to propanoic acid, so that's going to be 3 carbons as well, and I have OH. Right, that's what I want to get to. Again, we have a target in mind. Let's work backwards. Okay, let's don't try to go from this molecule all the way to this one going forwards, but let's actually work with we call these ones here precursors. What's the molecule before the one that you wanted? That's your target. So we have a carboxylic acid. There was only one way we learned to make a carboxylic acid. Earlier we had pulled it apart from an ester, but I don't have an ester here. So this is just an oxidized form of a primary alcohol. So this one can be created 1, 2, 3 OH like that. What are the reacting conditions needed for a oxidation? Again, acidified dichromate, heat, and reflux. Right? So I can do that process no problem. This is now my precursor. This is now sort of one step closer to it there. Okay. Now, you could, let me just do this on the side here, you could imagine, like I said earlier, well, now it's easy. Well, I just have a double bond and I want to add the water across. Let's just try to do that on the side here. If I had a propene, right, if I had this molecule here, and I end up trying to add a water across the double bond, right? We know the reacting conditions, right? The reacting conditions here, it's going to be in equilibrium. Reacting conditions are concentrated sulfuric acid, and I'm going to add a water. Water can be thought of as an HOH. Here's where Markovnikov here messes things up. If I'm going to add this electrophile here across the double bond here, the hydrogen is going to add to the carbon that has more hydrogens already attached to it. So the more stable one, let me just show it to you here. So carbon, carbon, if I add the hydrogen on this side, we end up forming our carbocation that's more highly substituted. This one here would actually be the major product. And in that case there, my major product unfortunately has 2 propanol, right? And yet what I want is I want 1 propanol. If I created 2 propanol and I tried to oxidize that one, that would only get to a ketone. That's not actually the carboxylic acid. So Markovnikov's rule here says this one only, adding water only creates 2 propanol when we want 1 propanol. So that's method is out. Okay, I can't think of, oh, just take this one here, add water, because that would actually put the OH on the wrong location. So now I need to come up with another method. Is there another way for me to actually get an OH group? Well, if it couldn't be an addition, maybe it could be a substitution. So if the OH here is actually a nucleophile, what would this one here have been substituted from? So maybe my nucleophile here was OH minus, so maybe I'm going to have carbon, carbon, carbon. I'm going to have CX. The X can be anything. I'm just going to put bromine on it just for argument's sake. There's more than one possible answer, right? But just based on what we know, we're just sort of working our way backwards. This one here was via the SN1 or SN2 mechanism. Can you predict for me which one is likely to be? This carbon here, right? The carbon involved with the functional group has one carbon neighbor. The other two are hydrogens. This is a primary alkene. So between SN1 and SN2, I would probably favor an SN2 mechanism. It's a one-step mechanism that it forms that 5-coordinate transition state here, flip of stereochemistry, all that again. Okay. And now I'm pretty close here. All right, so it's looking nicer. We didn't need to worry about the Markovnikov's part here and add water across. What I want to do here is I want to add a bromine. This is a halogenoalkane. A halogenoalkane could be from, I could try to add HBr, but same problem. The Br would be adding in the wrong location. So let's say I actually start off with just propane. If I just have an alkene, can I substitute it? Can I add it? Of course. This one here, you can add Br2 in the presence of UV. That was our free radical mechanism. So free radical mech. And then now we're pretty much done here. Well, I have propene, and I want to make propane, just working my way backwards here. This one I want to hydrogenate, so I want to add H2. This one we need nickel as a catalyst, slightly hotter temperatures, and you see by working your way backwards, you can actually figure out how do you get from one molecule to the other molecule. Again, not the only solution, but based on the steps that we learned in this chapter, that's one way of doing it. Okay. So practice a few of these questions here, and let me know if you have any problems. Thanks, guys.